Here we have a road which is fixed at one end and it is loaded at the other end with a force P. The length of the road is L. This is the x-axis. This end is x equal to 0 and the right end again is x equal to L. We know that what happens to this road is it will get displaced to the right. That is, every point in the road gets displaced towards the right. And here the problem is to find the displacement u at any arbitrary location x. We have to first mathematically model this problem. So we need a governing equation and boundary conditions. The governing equations can be formulated from equilibrium equations. These are the equilibrium equations for a 3D elastic problem. Here sigma x, tau xy, these terms are the components of stress. Fx, Fy, Fz are body forces. Since our problem is one-dimensional and if we neglect the body forces, we can write the equilibrium equation as d sigma by dx is equal to 0. That is this term alone. I have omitted the subscript x because there is only one independent variable. Still, this equation is in sigma. What we want is an equation in u, the displacement. For that, we need to convert the sigma to strain first, and then strain should be converted to displacement u. For that, we require stress-strain relations, or these are also known as constitutive equation. So stress and strain are related as sigma is equal to Young's modulus E into epsilon, where epsilon is the strain and sigma is the stress. We also require one more equation to substitute the strain to displacement. Since I've ran out of space, I will write it here. Strain is related to displacement epsilon is equal to du by dx. This equation is known as the strain displacement equation. Strain displacement equation. Now we can back substitute the value of epsilon in the stress strain relation, this one. So what do we get is sigma is equal to Young's modulus E into, instead of epsilon we have du by dx. Now we will substitute the value of sigma from this equation in the equilibrium equation. So what do we get is d by dx of sigma, which is equal to E du by dx is equal to 0. The Young's modulus is constant, E is equal to constant, therefore we can write this equation as E into d square u by dx square is equal to 0, or simply d square u by dx square is equal to 0. Now this equation is our governing equation. Governing equation. Now let us specify the boundary conditions. We know that at the left end, at x is equal to 0, the value of the displacement u is equal to 0. Okay, so our first boundary condition is at x equal to 0, the displacement u is equal to 0. For the second boundary condition, that is at x equal to L, we don't know the value of the displacement, but what do we know is the value of the load P. We can specify this boundary condition as at x equal to L, the value of the stress sigma is equal to P by the cross-sectional area A, if A is the cross-sectional area of the road. Here we have to notice that as the second boundary condition, we did not specify the value of the dependent variable. At x equal to 0, we specified the value of the dependent variable. So this boundary condition is known as the Dirichlet boundary condition. And since the value of the dependent variable is 0, this boundary condition is specified as homogeneous boundary condition, homogeneous Dirichlet boundary condition. Whereas the second boundary condition, we know stress is equal to Young's modulus into du by dx. So let me substitute this here. So here sigma is actually E du by dx is equal to P by E. Or we can write this as du by dx is equal to P by EA. So as a second boundary condition, what we are specifying is, instead of the dependent variable, we are specifying the value of the derivative of the dependent variable. So if you specify the derivative, then this boundary condition is generally called as Nyman boundary condition. Nyman boundary condition. Now we have the mathematical formulation of the problem. We have the governing equation and the boundary conditions. Now we can solve the problem as we have done in the previous case. We have to integrate this expression twice. So when you integrate it once, what we get is du by dx is equal to a constant c1, and after the second integration we get u is equal to c1 into x plus c2. Now in order to find the values of the constants of integration c1 and c2, we have to apply the boundary condition. The first one is at x equal to 0, u is equal to 0, and the second one is at x equal to L, the value of the derivative du by dx is equal to P by EA. So at x equal to 0, what we have is u is equal to 0, that is equal to c1 into 0 plus c2. This implies the value of c2 is equal to 0. And the second boundary condition is at x equal to L, what we have is the value of the derivative. So we will substitute that in this expression. So du by dx is equal to P by EA, and that is equal to c1. So we have the value of c1 also. C1 is P by EA. So a solution now is u at any value of x is equal to c1x plus c2. So c1 value is P by EA into x plus c2, we have already got this value as 0. So this is the solution. And if you want to find the value of u at any point, say for example at x equal to L, that is at the right end of the road, so at x equal to L, the value of the displacement u should be equal to P by EA into x is equal to L into L. This is the displacement. If you remember, this is the same equation that we have derived for axial loading case when you have studied mechanics of solids. That is delta, this is normally denoted as delta, the displacement at the end, is equal to PL by EA.